All right, so this next section is called complex zeros. So as you can see with the problems, it's going to be very similar to the ones we've already been doing, trying to find all the zeros. But now we're going to run into some zeros that are complex. So we have first here the zeros theorem, which some of you, we kind of already have talked about this a little bit, and some of you may have observed this on your own. But every polynomial of degree n is greater than or equal to 1. So really any polynomial has exactly n zeros. So whatever the degree is, that's how many zeros it has, provided that, and this is very important, a zero of multiplicity k is counted k times. So if you have a zero of multiplicity 2, that counts kind of twice. Okay, next up, the conjugate zeros theorem says that if a polynomial has a complex zero of a plus bi, then the conjugate a minus bi is also a zero. So we'll find all the zeros real or complex here. So I would, well, you can check synthetic, or you can check grouping here, but the ratio, whenever we have 4 terms, the ratio here to here is not the same as there to there, so the grouping is not going to work. So I just do my possible rational zeros, the factors of the number out back, which is 15, over the factors of the number out front. So we can try out 1 here. That is not going to work. So I'll go ahead and try out 3. And so it'll give me 1, 3, negative 4, negative 12, 5, 15, and then 0. So that one does work. So I have x minus 3 times x squared minus 4x plus 5. And so I can try to think of 2 numbers and multiply to 5 and add to negative 4. But actually, the numbers don't work for that. If you're thinking 5 or negative 5 and 1, that's not going to multiply to a positive 5. So I am going to have to use quadratic formula here. So I'm going to say x equals negative b, so that's going to be positive 4 plus or minus the square root of b squared minus 4ac all over 2 times a. So inside the radical there is 16 minus 20, so that's actually negative 4. And so 4 plus or minus, and then remember what I said in the last section here is that whenever we have a negative inside, we can just look at it as an I on the outside and then a positive on the inside. So the square root of 4 then is 2, so this is just going to be 2i. And so then if I reduce that, just dividing all of these by 2, I get 2 plus or minus I. So if I was to list out all the zeros here, I would say x equals 3, 2 plus I, and then 2 minus I. All right, next up here, number 2. So for this one, we have 5 terms, so grouping is never going to work. So I'm going to just go ahead and jump into my plus or minus 1, plus or minus 3 over plus or minus 1. So I like to try 1 first. So I'm going to do that. And yeah, that's not going to work because I can see it's just getting more and more negative here. So let's switch over to negative 1. Could have tried 3 as well. I don't know. So get 1, negative 3, 3, 1, negative 1, negative 3, 3, and 0. So that one did work. And the other thing I noticed is that I have 4 leftovers and they are in the same ratio. So I think factoring by grouping would work. So this would be x to the third minus 3x squared plus x minus 3. So I'll group those up. First group I can take out an x squared, leaving me with x minus 3. Second group I can take out a positive 1, leaving me with x minus 3. So I can write this as x squared plus 1 times x minus 3. And then I'm going to put the x plus 1 up here for the negative 1 that worked above. So I would solve the x squared plus 1 equals 0 over here. So if you take a square root on each side, then you would say x equals plus or minus, I would just call that I, because that's literally the square root of negative 1. So I'd say my zeros here are negative 1, I, negative I, and 3. They did put a graph here, and so I'm going to go ahead and graph it. And the big thing about the imaginary zeros is that they are not graphed on the real number plane. So I just graph the real zeros with that end behavior. All right, we're going to do some factoring here and finding all zeros. So 625, this is actually a perfect square. So I'm going to write that as the difference of perfect squares here. So I can get 25x squared and 9, 25x squared and 9, and we'll have 1 plus and 1 minus. Now, I think we all know that then we can break down the 25x squared minus 9 even further here by calling it 5x plus 3 and 5x minus 3, as that's the difference of perfect squares. Now, the other one here, you've kind of been told your whole life that you cannot break that down any further because it's the sum of perfect squares, but I'm here to tell you now that from now on you actually can break that down further when you have the sum of perfect squares. It's really going to be the same, and that's why I put this one first. It's going to be the same as the 25x squared minus 9, except that there's just going to be an I attached at the end. So watch how I do this. I'm going to do it 5x plus 3i, 5x minus 3i. And so that's my answer there for the fully factored form using i's. And the reason that works, if you kind of think about it here, if you multiply these back together, and you could actually do that using, I'm going to use a box here, so 5x plus 3i, 5x minus 3i. And we know that these are conjugates, so we can fool them anyway, but this would be 25x squared. These two would cancel out, that's the O and the I, so you could check them, but they're going to cancel out every time. And this would be negative 9i squared. Well, what is negative 9i squared? It's positive 9. So since they multiplied back together, we are allowed to factor that. And this actually allows you to see your zeros very easily. So we know this one's 3 over 5. This one's negative 3 over 5. And so same here, this one would be 3 over 5i. And this one would be negative 3 over 5i. So those are my zeros. All right, next up, number 4. Number 4 is a trinomial here, and the second power is half of the first power, so we are able to use a diamond here. So we're trying to multiply to negative 100 and add to negative 21. So that sounds like 25 and 4, with the 25 being negative. And you could use the grouping technique here. I'm just going to do the shortcut, but I know that it has to be x squared plus 4 and x squared minus 25 because it's got to multiply to that x to the 4th. And then we can actually break both of these down further. So this one's the old school one that you should have known before, x plus 5x minus 5. And then this is kind of the new idea, which is x plus 2i, x minus 2i. And so, like I said, with that x squared plus 4, just think of it like it was x squared minus 4. And then if it's plus instead, just put the I at the end. Okay, so that's the factored form. And then here is going to be our zeros. We got negative 2i, we got positive 2i, we got negative 5, and we got positive 5. All right, next up here, number 5, I got another trinomial, so I'm going to go ahead and do my diamond here. And we do have 36 on top for our a times c, and then 13 on bottom. So that sounds like, what is that? 36 is 3 and 12, right? That's not going to work. 4 and 9. Oh, that does work. Okay, so positive 4, positive 9. Now we do need to use the grouping here. So I'm going to put 4x squared and 9x squared there, plus 9. And then we'll group it up here. So we pull out an x squared, leaving me with, actually we pull out a 4x squared, excuse me, leaving me with x squared plus 1. And then we pull out a positive 9 here, leaving me with x squared plus 1. So we get 4x squared plus 9 times x squared plus 1. Now, both of these are the sum of perfect squares. And so when we're factoring them further, we just think about if it was a subtraction and we add an I at the end. So 4x squared plus 9 If that was 4x squared minus 9, I would go 2x plus 3, 2x minus 3. So now I'm just going to do 3I with that. All right, and then the x squared plus 1. If that was x squared minus 1, I would say x plus 1, x minus 1. So I'm going to say x plus 1i, x minus 1i, but I won't include the 1's there. So that would be my fully factored form. And then I would say x equals negative 3 over 2i, 3 over 2i. Then we have positive I, and we have negative I. All right, next one we have here is another trinomial. So for this one, we're going to do another diamond. So we have negative 8 on top, 7 on bottom. And so that's going to be I think that's a positive 8 and a negative 1. But I need to be x to the third in front of each of these. So x to the third plus 8, x to the third minus 1. Oh, I have an extra parentheses in there. That's all right. Okay, so I see both of these are perfect cubes, so I would factor them further with perfect cubes. So this one is x and 2, and then first parenthesis, we do x times itself, x times 2, and then 2 times 2. And then same, opposite, always positive. Okay, for the other one, we got x and 1, and then first term times itself, first term times second term, and then last term times itself. And then same, opposite, always positive. Okay, so I've been telling you guys that after the SOAP, that the trinomial back there never factors, and that is still true. But since we're looking for imaginary zeros now, I need to do quadratic formula on those. So I'm going to say x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And in fact, after the SOAP, not only are those not factorable, it'll always be imaginary zeros. So we're going to see that here. So let's see, this is 4 minus, that's a 4 in there. So 4 minus 16 is negative 12. Okay, so I know that that's going to be I rad 12, so I'm going to break down the 12 and look for twins. So we've got 2 and 2. So we're going to get x equals 2 plus or minus 2I rad 3 all over 2, which is just going to reduce to 1 plus or minus I rad 3 if I divide all of those by 2. Okay, so there's my zeros there. And so over here now, I'm going to list this as x equals negative 2. 1 plus I rad 3, 1 minus I rad 3. I know this one is 1, and then I need to do quadratic formula again for this one over here. So negative b plus or minus the square root of b squared minus 4ac all over 2a. It's negative 1 plus or minus the square root of negative 3 over 2. So that would just be negative 1 plus or minus I rad 3 over 2. Cannot reduce that one, so I'm just going to say negative 1 plus I rad 3 over 2, negative 1 minus I rad 3 over 2. All right, last up here, we're going to create some polynomials given zeros here. So we did this before. Now we're just going to include the imaginary numbers here. So it says the very important thing here is step 2, which is to create the zeros for the conjugates of the complex numbers. So on number 4 here, when they say we have a 0 at 3i, I know that there's another one at negative 3i. They don't have to tell me that. So that goes back to the first page of the section. It said the complex conjugate theorem. And so if a polynomial has the 0 at a complex number, its conjugate must also be a 0. So when I build this then, I'm going to do 3x minus 2 for the 2/3. I'm going to do x minus 3i for the 3i, and then I'll do x plus 3i as well. Remember the constant coefficient of 36, we'll take care of that at the very end. So now we're going to multiply together. Remember, we can do any order. So we definitely want to multiply the conjugates together first. So I do, because we can fool the conjugates, right? So I got x times x is x squared. And then last times last is, well, it's actually negative 9i squared. but remember that's going to turn into plus 9. And if you think back to the last page, kind of what we're talking about is that we could factor x squared plus 9 back into x minus 3i, x plus 3i, just the same as we would with x squared minus 9, just adding the I at the end, okay? So now we're just kind of going the other way with it. So now I need to multiply that by 3x minus 2, so that's just going to require one more FOIL here. So I get 3x to the third minus 2x squared, and then we get plus 27x, and then minus 18. Okay, so then lastly, they want that constant coefficient of 36. So right now my constant coefficient, remember that's the last number without a variable. Right now it's negative 18, so it sounds like I can multiply this whole thing by negative 2 in order to make it 36. So I get negative 6x to the third plus 4x squared minus, that would be 54x plus 36. So that would be my final answer there. Take care of that as the last step. Okay, so next up, number 5, same idea here. So when they give me that negative 2i is a 0, then that means that positive 2i must also be a 0. And oh shoot, this one should be degree 3. Sorry about that. Yeah, because we only have 3 zeros here. So I'll just do this one as 3x plus 1, and then x minus 2i, x plus 2i in whatever order you want. So then we will multiply those together. We can do the conjugates. So we get x squared, and then this one will be negative 4i squared, so it's going to be plus 4. Multiply that by 3x plus 1. So then that gives us a full FOIL here, 3x to the third, plus x squared plus 12x, and then plus 4. Okay, and then lastly, they want the linear coefficient of negative 6. So they want this one to be negative 6. So I'd have to multiply this by negative 1/2. So I'll go ahead and do that. And so that'll give me my final answer of negative 3 over 2x to the third, minus 1/2 x squared, minus 6x, and then minus 2. All right, next up, number 6. So this one gives us a complex 0 again. So that means we need to add another one here, even though they don't tell us. It has to be there, so it's going to be minus 3 minus I. So this one's going to set up as x for the 0 there, and then x minus 3 for this one. These complex ones now with 2 terms are a little more complicated. So here's how I write them. I write x minus, and then I write a bracket, and I write the whole 0. So we always do x minus whatever the 0 is. But in this case, since they have 2 terms, you got to be careful. And so I use a bracket for that. And so what that means is I'm going to have to distribute that negative. So what these are really going to become is x plus 3 minus I, and then x plus 3 plus I. So you can see here that, and this will kind of always be the case, is that the real part of the number will always be the same as each other in these parentheses and opposite of what they were up here. Whereas the i's, you just kind of need one of each. Okay, and so this one I'll call x squared minus 3x. Just distribute that x in. Definitely always want to multiply these ones together, because when you do that, the i's are going to go away. There's no cool little trick. If you find one, let me know. But I just kind of build my 3x3 box and multiply this out, kind of brute force here. So I'll go ahead and put this one down on the side and keep that one up top. So this will be x squared, 3x, ix. And I know that sounds weird, but hold up a sec, because I think that one might be getting canceled out somewhere. All right, so we get 3x, 9, 3i. Down here we get negative ix. As I said, that's going to cancel out. The negative 3i right here is actually also going to cancel out. And here I get negative I squared. Okay, so like I said, we do get to cancel a bunch of stuff out here, and those kind of boxes should always cancel out at those spots. This one down here, you should always be able to make into a real number. So that's negative 1i squared, so that's really plus 1. And so if I combine like terms here, I have my x squared minus 3x from the first parentheses, and now this is really x squared, combining like terms from my box, plus 6x, and then plus 10. So that whole thing turned into that. If you were to try to factor x squared plus 6x plus 10, it would not factor. If you use the quadratic formula, guess what you would get? You would get -3 plus or minus I. You would get back to here. We're not going to do that, though, because we're trying to expand here. So I'm going to go ahead and now build a 3x2 box. Put x squared minus 3x down here. So I get x to the 4th, 6x to the 3rd, 10x squared, -3x to the 3rd, -18x squared, and then -30x. So I'll combine like terms now. So we get x to the 4th, plus 3x to the 3rd, minus 8x squared, minus 30x. We didn't have any requirements for coefficients, so we are all done. All right, same idea here. So we got x plus 2 here. We're going to do x minus bracket 1 minus 3i. And then we know that the conjugate here, 1 plus 3i, is also a 0. So we're going to do x minus bracket 1 plus 3i. And so what we're actually going to be multiplying together here is x minus 1 plus 3i and x minus 1 minus 3i. So I'll do my 3x2 box here to multiply that out. Boom, 3i. Okay, so we get x squared minus x minus 3ix minus x plus 1 plus 3i. And this one would be 3ix. This one would be -3i. This would be -9i squared. Okay, so we'll cancel out, once again, those boxes. We can combine these two. And this one's going to turn into a plus 9. So we get x squared minus 2x plus 10 times the x plus 2 we had back up here. Multiply those together. Um, 2x squared, and then -4x, 10x, and then 20. So we get x to the 3rd. My x squareds actually cancel out. I get plus 6x plus 20. There we go.